Okay, what's interesting about the trig functions sine x and cosine x is their limit as x approaches infinity or negative infinity, those limits do not exist. And the reason is because you know that you should be familiar with these trig functions. Is basically all they do is oscillate between 1 and negative 1, and they just keep doing that. So they don't actually approach any particular number, they just oscillate between negative 1 and 1. Now an interesting function is sine x over x as x approaches infinity. And you can actually show that this limit is 0 by using the squeeze theorem. You know that 1 over x and minus 1 over x, that in other words you can show that the sine function is actually between, the sine x over x is actually between 1 over x and minus 1 over x. It's pretty simple. First of all, we know the sine function has to be within the closed interval negative 1 to 1, because that's the upper limit for the sine function is 1, the lower limit is negative 1. Well then, if you divide each of these by x, assuming x is just a positive number, so divide each of these by x, and you get minus 1 over x is less than or equal to sine x over x is less than or equal to 1 over x. Well, we know that from earlier discussion that the limit of 1 over x as x goes to infinity is 0, and the limit of minus 1 over x as x goes to infinity is 0. And since we have the sine x over x function trapped between the two, then that function must also go to 0 as x goes to infinity because of the squeeze theorem. Alright, let's look at an application. Suppose that f of t measures the level of oxygen in a pond where f of t is 1 is the normal level and time t is measured in weeks. When t equals 0, organic waste dumped into the pond, and as the waste oxidizes, the level of oxygen in the pond is given by this function. So here's your function, and it says what percent of the normal oxygen level of oxygen consists in the pond after 1 week, 10 weeks, and so forth. Okay, now remember t is measured in week. So to find the oxygen level at 1 week, just plug 1 in for t, and you get 1 squared minus 1 plus 1 over 1 squared plus 1, which is 1/2, or 50%. So after 1 week, the normal oxygen level is at 50%. But then if you plug in 10, the normal oxygen level goes up to almost 90%, or a little bit more than 90% actually, it looks like. But because you get 91 over 101, so that's about 90%. Okay, but then the question says, what is the limit as t approaches infinity? In other words, if you just let time keep marching on, then what's going to happen to this function? Well, you know that the limit of this function as x go, or t actually, not x, but as t goes to infinity, since the degree of the numerator is equal to the degree of the denominator, then we know this limit is actually just 1 over 1, the ratio of the lead coefficients. And so 1 over 1 is 1. So it should reach 100% oxygen level. Now, I'll let you just pause the video and read this definition. This definition defines limits, infinite limits at infinity, and this has to do with a function where when x goes to infinity, the function actually also goes to infinity, or negative infinity. So go ahead and look at this example. The limit of x to the fourth as x goes to infinity. Well, it makes sense that that function is going to go to infinity, because basically you would get infinity to the fourth, which is infinity. And if you have x cubed as x goes to negative infinity, well, you would be cubing very large negative numbers, and if you cube very large negative numbers, you're going to get a very large negative number. So this is going to go to negative infinity. So I've already told you that when the degree of the numerator is greater than the degree of the denominator, then the limits do not exist. But let's see if we can figure out a way to determine whether these limits go to infinity or negative infinity. The trick here is to simply look at the degree of the denominator. Look at the degree of the bottom. So if you look at the bottom, the degree is x squared. So if I divide this by x squared, that'll get rid of that variable. Well, dividing by x squared is the same as multiplying by 1 over x squared. So you can think of it either way. I'm going to either divide the top and bottom by x squared, or I'm going to multiply the top and bottom by 1 over x squared. It's the same thing. So if I divide x cubed by x squared, I'm going to get x. If I divide minus 1 by x squared, I'm going to get minus 1 over x squared. If I divide x squared by x squared, I'm going to get 1. If I divide 1 by x squared, I'm going to get 1 over x squared. Now, if you take the limit of these, well, the top is going to be, the limit as x goes to infinity, that's just going to be infinity. So you're going to get infinity, but remember, this goes to 0 and this goes to 0. So basically, you're going to get infinity minus 0 over 1 plus 0, which is really just infinity over 1, which is infinity. So this function actually goes to infinity as x approaches infinity. All right, let's do one more. Here the degree of the top is greater than the degree of the bottom. So in that case, here we got the limit x going to negative infinity. But notice the degree of the bottom is cubed. So this time I want to divide by x cubed. So it's whatever the degree of the bottom is that you're going to divide by. So I'm going to divide each term by x cubed. Well, x to the fifth divided by x cubed is x squared. X cubed divided by x cubed is 1. Minus 1 divided by x cubed is minus 1 over x cubed. Then on bottom, 5x cubed divided by x cubed is 5. And 1 divided by x cubed is 1 over x cubed. Now, these two terms are going to go to 0 when x goes to negative infinity. And then I'm going to get negative infinity squared. Let's see. Squared, right? Yeah, I'm going to get negative infinity squared. There's a typo here. So I'm going to get negative infinity squared here. So that's going to be negative infinity squared plus 1. So it's actually going to be plus infinity. Okay. If it had been cubed, then it would be negative infinity. But I'm going to get negative infinity squared plus 1 all divided by 5. And so that's going to give me plus infinity plus 1, which is basically just infinity over 5. So that's actually going to be plus infinity. So actually you can see, so if you graph these, you'll actually be able to see that this function as x goes to negative infinity is going to just increase without bound. And this function as x goes to positive infinity is going to increase without bound. Okay? Okay, let me go ahead and show you one more thing about asymptotes before we shut this video down. You can also get an asymptote that's called a slant asymptote. Now we talked about vertical asymptotes earlier, and then in this section we talked about horizontal asymptotes where you could get horizontal asymptotes. But there's also a situation where you can get something called a slant asymptote. Now actually you get a slant asymptote when you have a rational function, and if the degree of the numerator is only 1 greater than the degree of the denominator, then you can get what's called a slant asymptote. So for this example you would have a slant asymptote, and the same thing here. Here the degree of the numerator is 2. The degree of the denominator here is 1, so therefore you would have a slant asymptote in this case. Now, the way you find your slant asymptote is you just do long division. So we divide x plus 2 into 3x squared minus 1. So let's see how we do this. If you divide, you just say what times x equals 3x squared? Well, that's 3x, and then you multiply back. 3x times x is 3x squared, and then 3x times 2 is 6x. Well, remember, then you have to subtract this. Remember, long division, you subtract that. Well, then these terms cancel. Now, there's no x term up here, so I'm basically subtracting 6x from nothing. So that's going to give me minus 6x, and then I'm going to bring down the minus 1. And then I have to say, well, what times x gives me minus 6x? Well, that would be minus 6. So I add the minus 6 up here, and then I multiply back again. Minus 6 times x is minus 6x. Minus 6 times 2 is minus 12. Well, then you have to subtract. Well, if you subtract now, the minus 6x and the plus 6x will cancel, because remember, you're subtracting. And then you'll have minus 1 plus 12, which is 11. Well, you can't divide x into 11, so therefore all you're going to have left is the remainder 11. So basically what you found out is that this can be rewritten, this function can be rewritten as 3x minus 6 plus 11 over x plus 2. But here's the deal. As x goes to infinity, this term disappears because that term goes to 0. So all you get is 3x minus 6. And since 3x minus 6 is a line, then you can graph that line, 3x minus 6, as what we call a slant asymptote. And then you can see now how this graph approaches the slant asymptote. Now don't misunderstand. As x goes to infinity, the graph still goes to infinity, but it goes to infinity in such a way as it gets closer and closer to this line 3x minus 6. And the same thing in the other direction. As x goes to negative infinity, the graph actually does go to negative infinity, but it does so in such a way that it gets closer and closer to that line, y equal minus 6. Now also, what I didn't show you here, there's a vertical asymptote at x equal negative 2. So while I'm here, I might as well just go ahead and insert that. So there's your vertical asymptote at x equal negative 2, since the function is not defined at negative 2. Okay, so you have a vertical asymptote here and you have a slant asymptote. What you cannot have a slant asymptote and a horizontal asymptote in the same graph. So anyway, I just wanted to show you that because it just seemed appropriate to throw the slant asymptotes in this section. And I think I've got one or two more sections. I know we're going to talk about curve sketching, where we put all of this together that we've talked about in this chapter, and we try to sketch some curves using the information that we've learned in this chapter.